Okay guys, so I already made a previous video with the other class with period 7 and I already graphed a couple of these in that video, so I want to begin. I know this is a new class, so we're going to teach this lesson over again, but we're going to start with the other questions that we haven't done. So we're going to be graphing logarithmic functions. So let's start with number 4. Everybody go number 4. Right there we have a logarithmic function, y equals log base 3 of x. Now I want to graph this logarithmic function, but if we think about like an XY table, it's going to be very difficult to plug in numbers, right? Like even if you plugged in 0 for x, a 0 right there, log base 3 of 0, you're thinking 3 to what power gives me 0? It's all messed up, right? So let's not even go this route of doing inputs and outputs of a logarithmic function. Now, if we were to look at an exponential growth or decay function, that's a lot easier to do. And just a couple moments ago, we did find the inverse of a logarithmic function, and that ended up being an exponential function. The inverse of an exponential function is a logarithmic function, okay? So if I were to ask you to find the inverse of y equals log base 3 of x, let's just, even though this is not part of the problem, this is not part of your homework, but this is just so you could get a real good understanding of how we do this. If I were to find the inverse, I would switch x and y, and it would say x equals log base 3 of y. And then I would want to get y by itself. And to undo a log, you have to use an exponent. To undo an exponent, you have to use a log because they're inverses of each other. So if I were to want to get rid of this log base 3, if I raise this entire side to be the power of that base 3, then the 3 to the log base 3 would cancel out and the y would come down and be a regular y without a log. Does that make sense? Okay, but if I magically raise this whole side to be the power of base 3, then, and it's an equation, I better do the same to the left side. So I'm going to raise that whole side to be the power of base 3. So now we could clearly see that the 3 to the log base 3 of y, that eliminates and the y comes down and we end up with 3 to the x. So if I asked you to find the inverse of this guy, if I asked you to find the inverse of that guy, it would be this answer right here, y equals 3 to the x power. Do we agree with that? All right, now, is there an easier way of finding the inverse of a logarithmic function when there's no h and k? Yeah, there was no h and k on this one. It's really easy to do. It's simply getting your finger or something and covering this up. Look, it looks like y equals 3 to the x, which is the inverse of it. Pretty cool trick, right? Okay, very important trick. Do we understand that trick? Okay, I mean, if I asked you to find the inverse of this that does not have a h or k, yes, you're supposed to switch x and y the way we did up here, solve for y by applying exponents to get rid of logs, and you end up with this. But the quick and easy shortcut is to just cover up that log, and it looks like y equals 3 to the x, and that is the inverse function of the original. Do we get that? Okay, so let's go to graphing these logarithmic functions. So let's pretend that, let's just ignore this stuff, right? They want us to graph this guy. Now, if I ignore, like if I cover up this log and I actually find the coordinates to y equals 3 to the x, which is the inverse function of what we see here, right? If I actually find my coordinates to y equals 3 to the x, using consecutive integer inputs, -3, -2, -1, 0, 1, 2, 3, and I plug in the easiest input 0, what would that give me when I plug in 0 right there? Anything to the 0 power is 1, so my output is 1. And then I could use my growth factor, which is 3, to be able to find my other outputs. So 1 times 3 would give me the next output 3. And then times 3 is 9, and times 3 is 27. I'm off the graph. Now going in the opposite direction, if it's growing by 3 going this way, then backwards it's multiplying by the reciprocal of 3, which is really multiplying by 1/3. 9 times 1/3 is 3. 3 times 1/3 is 1. 1 times 1/3 is 1/3. 1/9, 1/27. Bottom line is it gets smaller and smaller and smaller. We should all know that from the previous lesson of graphing exponential growth or decay functions. Yay? Okay. So we have those coordinates of this exponential growth function. Should I graph those? No. Why not? Because these are the coordinates of the exponential growth function, not the logarithmic function. However, we do know that to find an inverse, what do? You switch x and y, then solve for y, right? So if you have the coordinates to this guy, which is the inverse of this guy, if you have the coordinates to this exponential growth function, which is the inverse of this logarithmic function, then you really have your coordinates over here. All you got to do is switch the x's and the y's. So the actual coordinates to your logarithmic function will be 1/27, which is practically nothing, -3. 1/9, which is still ridiculously close to 0, and then -2. 1/3, which is not even halfway, and you have a -1 over here for your y. So switch all of them. 1, 0, 3, 1, 9, 2. So we used the inverse, the exponential growth function, to find coordinates to be able to get the actual coordinates of our logarithmic function. That's the easiest way of doing it. So this right here, all this work is just to be able to get those coordinates, to be able to switch them to get our actual coordinates. So I would put a line through these guys so you don't get confused and start graphing those, right? We now have our actual coordinates over here. So let's plot these points. And it does get a little weird since we're so used to graphing exponential growth and decay functions. Check it out. Let's go to the coordinate. Let's go with an easy one, 9, 2. So let's all go 9 on the x, 2 on the y. There it is. Let's go to the next one, 3, 1. This guy right here, 3, 1. So we're going to go 3 on the x, 1 on the y. There it is. Let's go to the next one, 1, 0. 1 on the x, 0 on the y. There it is. Let's go to this one. This one's where it gets a little weird. 1/3 on the x and then -1 on the y. So you're at 0, 0. When you go 1/3, it's not even halfway. It's only 1/3 of the way and then -1. So it's really close to the y-axis. Let's put that dot right there at 1/3 and then -1. And then the next coordinate is 1/9, which is even closer to 0, and then -2. So you're at 0, 1/9. It's kind of even hard to draw the difference. 1/9 is super close to 0, but you're going to go down to -2 right there. And then the next one, 1/27, man, that's still even closer to 0, but you can't actually draw the difference between 1/9 and 1/27. So it looks like it's actually on the y-axis itself. Does that make sense? And we could continue to get closer and closer and closer and closer to that y-axis, which means that the asymptote is what? The y-axis. So this is your asymptote, and here's your graph. You draw it like if it's actually on the asymptote, the y-axis, and that asymptote, you could also call it x equals 0. That's how to get a vertical line through the x value of 0, which is the y-axis. X equals 0 is your asymptote. And that's how we graph logarithmic functions. That's how we graph logarithmic functions. Now, what if I would have had an h and a k? Well, then I would identify h and k, and then box in the function and go through everything that I just did. Get the coordinates for the exponential growth or decay function, switch them to get x and y, and if I did have an h and k, I would then shift my coordinates according to h and k to get my final product, my final graph. So flip it over to the back side. Let's look at number 7. That's the hardest one there is, pretty much. So the steps would actually be, I know you guys love steps, right? That way you could just follow them without thinking. Step 1, identify h and k, ignore h and k by boxing in the function. Step 2, cover up the log, get coordinates of the exponential function, which we know is technically our inverse of that logarithmic function. And then switch x and y values to get the actual coordinates of log function and graph and shift according to h and k. So it is a lot, but your steps are right there. So let's do what we always do for step one. Let's identify h and k. What is h? What is k? H is 2, which means we're going to shift 2 to the right. K is 3, which means we're going to go 3 up after we get our coordinates of the logarithmic function. So once we identify h and k, we box in the function without the h and k, ignoring h and k. And we're really going to graph this guy. But it's hard to graph logarithmic functions. It's easier to graph exponential growth or decay functions. So I am going to graph the inverse of this, not by doing the math of switching x and y and solving for y. I mean, I could do that if I wanted to, but it's a lot easier. The shortcut is to just do this. Cover up that log, and it looks like an exponential decay function. It looks like it says y equals the fraction 1/3 to the x power. And that really is, y equals 1/3 to the x power really is the inverse of y equals log base 1/3 of x. It really is the inverse. So I am going to, whoa, what happened there? Sorry. I'm going to make an xy table for the coordinates of the exponential decay function y equals 1/3 to the x. So I'm going to use consecutive integer inputs, -3, -2, -1, 0, 1, 2, 3. Plug in the easiest input, 0. When I put 0 right there, anything to the 0 power is 1. When I plug in 1 right there, actually let's use the 1/3, the decay factor, to make this output decay by 1/3. So 1 times 1/3 is 1/3. 1/3 times 1/3 is 1/9. It decays down to 1/27 on the last one. And going in the opposite direction, to be multiplying by the reciprocal of the decay factor, which is multiplying by 3. So 1 times 3 is 3, times 3 is 9, times 3 is off the graph. Anyway, we have those coordinates, but those coordinates are the coordinates of the exponential decay function, not the actual logarithmic function. The actual logarithmic function, we're going to get those coordinates how? By switching the x and the y. Why? Because this is really the inverse of this, and to find the inverse, you switch x and y. So we're going to take these x and y values and we're going to switch them, thus giving us the coordinates of the actual logarithmic function, which is the inverse of this exponential decay function. So our actual coordinates will be 27, -3. I can't even graph that. 9, -2. 3 and -1. 3 and -1. I almost wrote that wrong. 1, 0. 1/3 and 1. 1/9, even closer to 0, and 2. 1/27, even closer to 0, and 3. So those are our actual coordinates. Once you have your actual coordinates, you could just scratch that out so you don't make the mistake of graphing those. Let's plot the points. 3, -1. 1, 2, 3, -1 is right there. 1, 0. 1, 0 is right there. How about 9, -2? Let's go all the way to 9, -2, it's right here. Let's go for the more confusing ones. 1/3 on the x, 1 on the y. So 1/3, it's not even halfway, but you do go up on the y, so you're right there, 1/3 and 1. And then 1/9 and 2, it's even closer to 0, but you go up to 2. So at this point, it looks like you're actually drawing right on the y-axis itself. Now, if I graph this, I would technically be wrong because I still need to do what with these coordinates? H and K. Move them 2 to the right and 3 up. So every one of these gets moved 2 to the right and 3 up. So this guy that's over here closer to the edge, I'll move 2 to the right, I'll be off, and then 1, 2, 3 up. Let me put, even though I'm off the graph, I'm going to put it right here. And then let me go to the other ones. This one, 2 to the right and 3 up, 1, 2, 3. And the next one, and so on and so on. By the way, if our original asymptote was right here at x equals 0, where's our new asymptote going to be at? It's not the k value because it's actually going to be x equals 2, right? Your h value. So if you go to x equals 2, 1, 2, and put your asymptote right through the x equals 2 line, that's going to be your final asymptote, which helps you out a lot because as you draw your dots going this way, you know it's going to infinitely approach that but never actually touch it. So there's a 1/3, there's closer, closer, closer. You draw it like if it's actually touching your asymptote, bless you, of x equals 2. So here's our graph. Now let's take it a step further. Let's talk about domain and range, ladies and gentlemen. The domain are your x values. Is the domain x equals all real numbers? Not on this one, not on this logarithmic function, not on this blue graph. Because your x values run left and right, and if it were x equals all real numbers, that would mean that this blue graph goes to the left forever, and we know it doesn't. It infinitely, from right to left, it infinitely approaches the x value of 2. So how could we state that this entire blue graph is on the right side of the x value of 2? How could we state that as an inequality? X is greater than 2. How about the range? The range are your y values. Y does equal all real numbers. It's not that it's above a certain value or below a certain value. The y's go up forever, right? If you're going this way, it's right here, it's at the level of 2, 3, 4, 5, 6. It keeps going up forever. And even though it curves this way, it still continues to go down forever. So it really does go up and down forever. That's why the range, the y values, are y equals all real numbers. Now we could take this a step further and talk about or write end behavior notation. As x approaches, let's say, negative infinity, your y values, your f of x values approach what?
1. Wait.
Now what does this mean really? Look at it to the left or to the right? Look at it to the left, right? Here your x values are left and right, and this is saying look at it to the negative infinity. Well, if you're from the right going to the left, does it ever go in this direction? No. Right here, the y value is 1. Right here, the y value is 2. Y value 3, 4, 5. So as you're going to the left, it's going up forever. So that'd be positive infinity. As x approaches positive infinity, your y values approach what? As you look at it to the right, to positive infinity, where are your y values going? It's still going to infinity, but in the negative direction. Now, that's not an actual thing that I ask you to do, but it's good to be able to look at that graph and fill in those blanks when you're talking about end behavior. So once again, let me reiterate what we're doing here. We're graphing logarithmic functions, and the steps to graphing logarithmic functions are right there. Identify h and k, ignore it. That's the same first step as always. Ignore h and k by boxing in your function without h and k. Cover up the log. That way it looks like an exponential growth function or decay function, which will technically be the inverse of the actual logarithmic function that's boxed in. And this is why we switch x and y. Once we get the coordinates, we switch x and y because they are inverse functions. You switch x and y, you'll get the actual coordinates of your log function, graph it, but if you have an h and k shift, make sure you shift your final coordinates according to h and k. And of course, not all of them are logarithmic functions. Some of them are review exponential growth, review exponential decay. Should we do another one? Should we do number 6? Doesn't have an h and k. It's pretty easy. Or do you guys want to take over?
Yeah.
You want me to do it?
Mm-hmm.
No? You guys got it?
Yeah, we got it.
All right. You guys got it.